Hello everyone, uh, Eddie here again. In this video, I'm going to talk about how to understand torque and speed in mechanical drives. So this is a principle that's essentially going to be true regardless of whether I'm dealing with a gear drive, which is when you have like a series of gears, like so. Or we could have a belt drive, which is where we have a sheave, or sometimes you hear it called a pulley, with a belt running through it. So it'd be like two pulleys connected with a belt. And we could also have a chain drive, which is when we have a sprocket, is what we call it, which looks sort of like a gear, and there is a chain that runs through the sprocket, and it's connected to another one. So if you think of like your bicycle, all of these are examples of mechanical drives. The goal is to transmit motion from one shaft to another. So each of these can be connected to a shaft, which is like a spinning cylinder that'll turn along with uh, the sheave, the gear, or the sprocket. They all have kind of different applications. I just want to explain that the basic principle applies to all of them. And this is going to be about ratios. So the general formula here is that power, you can think of this as watts or horsepower, is going to be equal to the torque, which is, you can think of this as the twisting force. So, for example, if I am trying to open a really stiff uh, jar, like a, think of like a jam jar that's really hard to open, I need to twist it really hard. That's a high torque operation. I have to twist it super hard. And so, power is part of it's how hard you're twisting, and the other part is the speed or how fast you are twisting. So with mechanical drives, we can adjust our torque and our speed. And the classic way to think about this is in a car. So when the car starts, it's at a stopped position. In order to get it moving, you need a lot of twisting force, a lot of torque to get it going. But then after it gets going and overcomes the inertia, it's then possible to increase the speed. You don't need as much torque, so you can convert the horsepower in the engine to speed by changing the gear ratios. And that's the basic idea here. So when we talk about gears, sheaves, belts, sprockets, chains, all of that, the same principle applies. And it basically is this. If I have two gears, I'm not very good at drawing gears, so I'm just going to ask you to bear with me. So this gear has 6 teeth, and I have this gear, which is a larger gear, I'm not drawing this well, but it looks like I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 teeth. I was shooting for 12. I'm not a very good artist. That's okay. If I were to fit these together, if this is my driving gear and this is my driven gear, meaning that this is like connected to the motor, so it's spinning by itself and it interconnects with this other one to spin it. That's what driven means. What's going to happen is that whichever one has more teeth has higher torque and lower speed. So let's say um in this case we have a ratio of 6 to 10, which would be 10 divided by 6, so that's going to be 5/3. Um with this means I'll just do this 1.67 torque is going to be multiplied by 1.67 and the speed is going to be divided by 1.67. Um so that's basically how this works. So um if I go from this gear to this gear, this one's going to have a higher torque and a lower speed. And it's going to be the ratio of teeth in the output gear over the teeth in the input. And that's going to kind of determine how it all changes. So the reason they both change is the total power pretty much remains the same. There's a small amount of power loss when we go from one gear to the next, but it's pretty efficient, so that's very minimal. So that's the basic idea of how this will all work. So if for example, um I had a torque of 10 foot-pounds, the new torque would then be 16.7 because we'd multiply by the 1.67. If my speed was um 1700 RPM, rotations per minute, that would go down to approximately 100 because we're again dividing. Actually, it'd be about 1,000 because we're dividing by 1.67. So um that's just basically how that's going to work. So the force goes up, the speed goes down. And if we reverse the process, like if I go from the big gear to the smaller gear, it's going to be the exact opposite where the force goes down and the speed goes up. So it both of them are always kind of going to be going at a certain speed and a certain force based on the total horsepower. It just depends on which one is the driving gear and which one's the driven gear. So if you go from a big gear to a small gear, the speed's going to increase and the force is going to decrease. If you go from a little gear to a big gear, it's going to be the opposite. Force goes up, speed goes down. And this is true when you're dealing with pulleys and sheaves in a belt drive. Whichever one's bigger has more force and less speed. And Same with sprockets and chains. In a chain drive, the bigger one is going to have more force and less speed, and it's all going to be proportional to the number, like basically the size of the two. So if it's a lot bigger, it's a much more dramatic difference. If they're close to the same size, the force and speed are going to be really similar. So that is basically what you need to know in terms of how uh, gear ratios, um, sheave ratios, and sprocket ratios work for mechanical drives.